taking a high-fidelity digital concept, like the intricate AI-generated designs found on Reticle-red.com, and carving it permanently into physical metal is a rigorous test of thermal management. You're essentially blasting a canvas with concentrated heat, requiring the material to survive the transition from data to steel. The standard tool for this process has long been the Q-switched fiber laser, the traditional workhorse of the marking industry. These systems rely on cavity gain disruption. The laser cavity traps energy until it reaches a saturation point, then releases it in a high-intensity burst. While powerful, this architecture produces a fixed-width pulse, typically constrained to a narrow window between 80 and 140 nanoseconds. For deep engraving or heavy material removal on thick industrial plates, this high-energy delivery is a primary advantage. However, that same intensity becomes a liability during complex renders. On delicate substrates, the fixed pulse duration transfers excessive heat, often warping the metal or blurring the microscopic details of the digital art. This graph illustrates the central thermodynamic limitation of Q-switched hardware. As the repetition frequency increases on the horizontal axis, the peak power on the vertical axis crashes. This happens because the gain medium needs time to recover its energy between pulses. When the laser fires faster, the time between shots shrinks, and the individual pulses become progressively weaker. This inverse relationship means an operator cannot increase the marking speed without losing the intensity required to initiate a clean mark. In practice, this lack of independent control ruins sensitive jobs. It leads to uncontrollable bubbling on plastics and prevents the smooth, high-contrast annealing required for titanium medical components. You eventually hit a physical wall. Attempting to force higher detail or faster throughput leads to unwanted melting and internal structural stress within the substrate. Modern manufacturing completely bypasses this inherent limitation by using the master oscillator power amplifier, commonly known as the MOPA architecture. MOPA separates the entire process. A master oscillator generates a low power signal with specific temporal characteristics, routing it through power amplifiers. This decouples pulse duration from repetition frequency, making the beam's contact time an independent variable without affecting pulse energy. The resulting operational window is vast. While Q-switched lasers are generally limited to 200 kHz, MOPA systems maintain high peak power at frequencies up to 4,000 kHz. By controlling these variables independently, the process evolves from simple material removal into the precise mathematical programming of thermal energy. This enables cold marking. Shortening the pulse width to 2 nanoseconds concentrates energy into a brief window, preventing heat conduction. On aluminum, these rapid bursts ablate only the top anodic layer, creating a high-contrast dark mark, while the underlying substrate remains completely cool and unaffected. This nanosecond-level thermal control is required to translate the incredibly fine detail of custom artwork from Reticle-red.com onto metal surfaces without any fidelity loss. Conversely, expanding the pulse width to 500 nanoseconds allows for controlled heat pooling, which is necessary for the chemical transformation of the metal surface. This achieves color marking on stainless steel. By timing long pulses to hit specific temperatures between 800 and 1500 degrees Celsius, the laser grows a nanometer-thin oxide layer. This film creates thin film interference, refracting light into vibrant hues of blue, gold, and green. This allows for the painting of industrial metals using only light and atmospheric oxygen, with this specific color determined entirely by the machine's numerical parameters. Advanced MOPA hardware is now moving past visual identification into functional surface modification. In aerospace applications, controlling the precise overlap of laser pulses regulates the residual stress within the material. This precision suppresses the formation of columnar crystals, preventing cracks in brittle, high-performance alloys. By varying the hatch spacing and frequency, the laser alters a metal's wettability. It restructures the surface at a microscopic level to make it either actively repel or attract fluids. This degree of thermal programming transforms the surface from a static identifier into a functionally engineered component, optimized for specific industrial environments. Maintaining stability requires navigating the power reduction frequency point, the threshold where average power begins to drop. The JPT M8 series compensates for this with a peak power of 50 kilowatts, enabling it to initiate absorption in materials like glass that usually require a different laser wavelength entirely. Modern manufacturing has moved from the blunt force of early hardware to a refined, highly adaptable thermodynamic science. This level of hardware control ensures that digital creativity, from industrial schematics to custom designs on Reticle-red.com, no longer faces a physical bottleneck during production. The MOPA laser ensures that whatever we can model digitally can be perfectly rendered and engineered into solid steel.